I'm Alex. I'm an assistant professor at the Universidade Nova de Lisboa, New University of Lisbon in English. Today, I'm going to be talking about some relatively recent work joint with Martin Albrecht, Amit Dio, and Daniel Gardam. This work is entitled Crypto Dark Matter on the Torus, Oblivious PRFs from Shallow PRFs and FHE. Broadly speaking, I'm going to be talking about a construction of an oblivious pseudorandom function protocol, and particularly based on fully homomorphic encryption and Torus fully homomorphic encryption. Hang on. There we go. So for those of you that maybe don't want to sit through the entirety of this talk, I've got like a too long didn't read slide here. So in this talk, I'm going to be presenting a post-quantum candidate of an oblivious pseudorandom function protocol. So these protocols have existed for quite a while. Recently, there have been various applications in the real world setting that have made these quite interesting. So the Internet Engineering Task Force has started standardizing these protocols based on classical group assumptions. These protocols based on classical groups are very efficient, and they're used for kind of like authorization settings in the internet, broadly speaking. So I'm going to be talking about these applications during the talk. In this talk in particular, I'm going to be focusing on post-quantum candidates. So the interesting thing about post-quantum candidates is that they're not quite yet as efficient, or even more accurately, they're not even anywhere close to being efficient enough for kind of like the intended applications. So with this in mind, my co-authors and I kind of like, we've worked on these constructions in the past, but we kind of wanted to analyze the setting in the FHE setting, or from FHE-based primitives. So in particular, we construct new candidates of these oblivious pseudorandom function protocols from low-depth pseudorandom functions, and specifically using Torus FHE. These protocols have various kinds of security properties which are interesting. One of these is verifiability. Again, I'm going to talk about this during the talk. And we have some quite what we think are interesting heuristic arguments for achieving verifiability without going down the route of having very expensive zero-knowledge proofs. Cryptographers might say that heuristic arguments are not really cryptographically secure, but I'm going to talk about the basis for these arguments in the talk. The kind of take-home message of this talk is that while our construction is actually more efficient than previous post-quantum candidates, efficiency is still behind classical counterparts. And so this work, in effect, motivates the continued study of these protocols. So for those of you that are kind of uninitiated in this domain, I'm going to start by talking about oblivious pseudorandom functions and their applications in general. So in this setting, we have a client that holds an input X and a server that holds an input GK. What we're trying to achieve here is for the client to be able to evaluate a pseudorandom function, which is like a classical cryptographic object on the server's key K and their own input X. So what these protocols involve generically is some amount of communication between these two parties. This can go on for multiple rounds, but we call these protocols round optimal if there's like a bilateral exchange of one message each way. And in the end, what the client should output is a pseudorandom function evaluation on these two values. So the security properties for these protocols, the core security properties are that the server learns nothing about the client's input X, and the client learns nothing about the server's key K. Okay, they're the two key things to remember. We've also got some extra properties. So there's a property known as verifiability. Verifiability ensures that the server always proves that the output of the computation was evaluated using the key K. So we can kind of think of this as like a malicious security notion if we talk about this in the like multi-party computation security framework. In essence, the client learns that rather than like in the standard OPRF, the server could actually return random garbage, and due to the security properties of the pseudorandom function, you wouldn't be able to tell whether this was random garbage or the actual real output. And this proof ensures that the client knows that they actually have a pseudorandom function evaluation. Typically, these constructions require some sort of initial public commitment C or a public key related to the server's key K, and these are known as VOPRFs for short. There's also another property which is known as partially oblivious pseudorandom functions. In this setting, there's kind of some public metadata available to both the client and the server. And there's some way of injecting this public metadata into the computation itself. So the pseudorandom function is evaluated not only over the key K and the input X, but also somehow over this associated data. And there are various kinds of applications for why this is important. I'm not going to talk about these here, but these are known as POPRFs. So in terms of some concrete applications, as I said, the Internet Engineering Task Force has taken kind of an interest in these protocols. So there's actually very soon there's going to be an Internet RFC for specifying verifiable oblivious pseudorandom functions in prime order groups. So that's quite classical setting. And one particular application that's seen a lot of industry usage, so used by Cloudflare and WhatsApp and the Brave browser, is this protocol known as Privacy Pass. Essentially, Privacy Pass is a VOPRF protocol, but just to kind of talk about it generically, we're in the VOPRF setting, so the client knows of some commitment C to the server's key K, and they send a blinded token. This is kind of like the VOPRF. This is essentially like the first message in a VOPRF. The server responds by evaluating sort of homomorphically the pseudorandom function over this blinded token. And the client outputs like an unblinded version of this token that still preserves the like pseudorandom homomorphic evaluation, or it still preserves this homomorphic pseudorandom function evaluation over the VOPRF output. So this is kind of like an unblinded thing. And what Privacy Pass does is in the future, you can kind of reveal your initial inputs and you can reveal this token. The server can ratify it, it can authorize it, and these tokens then can be used to kind of gain authorization to things. So Privacy Pass is typically used to grant unlinkable authorization. So here, when you do this unblinding step, you unlink the token from the issuance event. And then in this step, when you kind of do a redemption event, the server can tick yes or no. And you can kind of use these as kind of like one-time cookies that allow you to navigate across the internet in kind of an unlinkable way, whereas like global cookies or third-party cookies kind of do this in a linkable way. So clearly there's like privacy improvements to be gained from these constructions. So another application, again, that the IETF is taking an interest in is OPAQUE. So OPAQUE is a password authenticated key exchange, or OPAQUE. PAQUEs essentially use a client password to build a key exchange protocol and allows mutual authentication between the client and server, such that the password domain is protected against pre-computation attacks. And they use generically an oblivious pseudorandom function protocol and an authenticated key exchange on top to build these secure PAQUEs. And again, there's various applications. One of them is that passwords, are typically quite faulty, and that also the storing of passwords is quite a careful endeavor. You don't want to store, if you reveal kind of like database of passwords, it can be very serious, for the people's data that's included in that in those databases if there's a data breach. And so if these protocols kind of allow you to still have password-based authentication while kind of hiding the password dictionary even from the server, which is quite nice. So I'm going to just move on to talking about kind of the core idea of our work here without really getting too much into the details. So previous post-quantum oblivious pseudorandom functions are based on two types of primitives. So first, there was some work by Albrecht et al. At PKC in 2021, where they build oblivious pseudorandom functions and verifiable oblivious pseudorandom functions from ideal lattices. Essentially, they take classical primitives and kind of like naturally convert them to a ring LWE setting, and the security of their work is based on both ring LWE and the one-dimensional short integer solution problem. And they build a protocol that satisfies verifiability. They require zero knowledge proofs based on lattices. The problem with these constructions is that performance is very, very poor. The bandwidth is very high, and the computational costs are very high as well. One of the key reason, well, there are two key reasons for this. One of them is that in the classical setting, for reasons I'm not really going to get into, you can kind of avoid a lot of these zero knowledge proofs because the structure of the group allows you to get away to essentially rely on the fact that the client can't cheat, and the server's capabilities are quite limited as well. In the ideal lattice setting, because lattices kind of permit these like natural trapdoors, you have to work a lot harder to prove that a malicious party can't controvert the security of the protocol. So there are a lot more zero knowledge proofs that are required, so that's one thing. And also there's some kind of noise flooding arguments that are required for protecting certain key material that kind of gets encoded into the noise. And so here there's a lot of parameters are not quite as efficient as we would like to be in the lattice setting, or at least not as efficient as kind of like practical lattice-based cryptography. In the isogeny world, there's two lines of work. So Benet et al. In Asia Crypt 2020 provided the first construction of Oblivious pseudorandom functions from isogenies. Some of they presented multiple constructions. Some of these were based on assumptions that were later turned out to be insecure. They have one construction based on Seaside, I believe, which still retains security, but the parameters are kind of different to what they've originally said. So the performance is harmed. Antonio Basso's work at SAC in 2023 kind of improves kind of the state of the art in the isogeny realm, bases things on new assumptions and achieves better performance, but still performance is not quite there with classical schemes. And I'm not really an isogynist, so I don't want to say anything too out of line, but the security guarantees in isogeny-based crypto seem a little bit more unsteady or a little bit less static than the lattice-based setting. So I should also state that the caveat that I'm very much more on the lattice side of things. So it's natural for I and my co-authors to kind of stay in that kind of setting. So I'm going to talk about generically our idea for this construction. I'm going to, given that I'm at an FHE meetup, I took the liberty of not explaining what an FHE scheme was. I'm going to assume the audience knows those things. So broadly speaking, our protocol is very, very simple. We kind of saw the state of the art and we said, what if we just built the most simple OPRF we could from FHE, and what would this look like? So the client has their input X. They're also going to have this additional input, a secret key SK. So we're in the secret key FHE setting. All the client does is encrypt their input X using this FHE scheme. They get this ciphertext, they send it to the server. This is kind of like the blinding step. And then in the second step, the server evaluates the pseudorandom function and with their key K as an input as a circuit on the plaintext domain of this FHE scheme. So on this input X, which is encrypted, and they get a new ciphertext CKX. They can do this publicly. Sorry. And they return this to the client, and the client decrypts this ciphertext using their secret key and essentially learns the pseudorandom function output. So this may seem like a really simple idea, and you might ask, if this is the idea, or how come no one had done this before? And that is a very good question. It's not totally clear to me why that wasn't the case. My conjectures are that FHE in the past 2 or 3 years has actually seen a lot of performance enhancements, particularly with TFHE, which I'm going to talk about. And I think before that, kind of these kind of constructions where you evaluate fairly complicated circuits, especially like pseudorandom functions, which are based on HMAC or AES, we're not quite at the stage where we thought we could build these kind of schemes. But there are also a number of other interesting problems, which I'm just going to raise now. So one thing is that particularly in the lattice setting, the lattice kind of ciphertext, which are usually ring LWE samples, broadly speaking, or learning with errors samples, can have trapdoors in them. They can be kind of badly formed, and it's difficult to know when that is the case. So here, really, this client also not only has to send their ciphertext, they have to send some sort of proof that this is a well-formed ciphertext. Because if this ciphertext is going to have the pseudorandom function evaluated over it, which includes the server's key K, and if this ciphertext was formed badly, then there may, in theory, be some way of leaking the server's key K, given some sort of structure. On the return, achieving verifiability, you could say generically we could achieve using like some non-interactive zero-knowledge proof or SNARKs or something, but using snarks to prove FHE computations, as far as I know, and again, I'm not really an expert on snarks, is still a fairly expensive endeavor. These protocols, just to kind of reiterate, we expect them to be very, very efficient. In the classical setting, they evaluate in like a matter of milliseconds, and the amount of communication is a number of bytes. And I think this sort of computation would be kind of out of the realms of snarks. And kind of as an open question, one of the key things is like, how expensive is it to evaluate a PRF, and how do you choose a PRF to evaluate that on the encrypted ciphertext? Because the choice of PRF is really going to impact how expensive this scheme really is. Okay. So with those questions in mind, I'm going to move on to our kind of specific construction. So I'm going to start with a very, very nice work from Benet et al. TCC 2018, where they propose kind of a conjectured weak PRF. And so what you may notice during this talk is actually there's a lot of like conjectures flying around. We're kind of on the edge of, what's assumed to be secure and what's not. There aren't so many, standard assumptions in this work. We're kind of really kind of pushing the boundaries in order to try and get high performance. So as I said, there's this PRF from Benet et al., a low depth weak PRF. So what this PRF does, it takes a matrix A. This is the key of the pseudorandom function. And it has very low dimensions, so it's like dimension 256. The input is a vector with dimension 256. It's a binary vector, so A is completely binary, X is binary. You multiply A and X together, and you take the result mod 2, so this vector, and then you take the inner product of this vector with the all1 vector to get some kind of synthesized output. But you reduce this output modulo 3. Okay, so this output Z is the output of the pseudorandom function. The key thing to remember here, there's not really a security assumption, like we can't reduce this to LWE. There's no statistical security argument. This is a conjectured secure weak PRF. And a weak PRF, for those of you that aren't aware, is one where the input X is actually sampled uniformly at random from the input domain. So here, we can't specify our own input. This is kind of like a non-interactive pseudorandom function. So we start from this point and we analyze whether there's a possible way of embedding this pseudorandom function into an FHE kind of evaluation. So if we wanted to turn this kind of into the weak OPRF in FHE, we have to analyze kind of which parts are going to be evaluated where. So this matrix A is going to be the service secret key. Z is going to be the OPRF output, the output of the pseudorandom function. And the input X is going to be from the client. The client's going to have to send this encrypted in some way. But actually, we don't have to encrypt anything else. We can everything else can be performed in the clear. A is kind of like a binary, almost like a lookup table on X that just tells you in each row multiplication which ciphertext in the entries in the encrypted vector of X to add together. And then the rest of the operations can be performed again, like arithmetically. And then to receive the input, the output Z, you simply decrypt the vector in each element, and then you get the output. So naively, concretely, the number of multiplications here is going to be roughly quadratic in the dimensions of A, and you're going to have some number of additions as well. The crucial thing with this pseudorandom function that's not quite that makes it nice or more well suited to kind of Torus FHE is that, as you can see on this slide, we're kind of moving from a plain text modulus of 2 to a plain text modulus of 3. And here, in order to do this, to make this transition work, we actually have to evaluate some nonlinear function. Obviously, we can evaluate any kind of function in FHE circuit, but one of the nice things about TFHE is it has this programmable bootstrapping paradigm, which means that essentially every time we do a bootstrapping operation, we can also evaluate some generic function over the plain text domain as well. And this is specifically nice because it gives us a nice way of evaluating these functions very easily without having to write the full circuit out. And essentially, because these moduli are quite small, we can do this using lookup tables quite efficiently. So just to kind of be concrete about my expectations on the programmable bootstrapping function, we have an encryption of X under some secret key. We have a bootstrapping key BSK. We input both of these things to this kind of classic black box, and the output is an encryption of under a potentially new secret key, SK prime. It could also be the same secret key if you do some sort of like clever key switching. But the encryption is actually a function of X rather than X itself. And this F is some generic function that you implement in this programmable bootstrapping. So here I'm going to use the acronym PBS to refer to this kind of operation. And we specifically use it to perform modular reduction and switching. So that was a weak PRF. We actually need, in the OPRF setting, we obviously need the client to be able to specify their own input. So we need to move to a full PRF. Unfortunately, Benet et al. Come to our rescue with a low-depth full pseudorandom function. So I'm just going to talk that this pseudorandom function is a bit more involved. So I'm going to talk through the various steps and how we map these to the OPRF setting. So firstly, we still have the input X. This has dimension 128 now. And we have this public matrix GIMP, which you can think, it's not actually like this, it's a bit more structured than this in reality, but for the purpose of this talk, you can think of it as a uniformly sampled ternary matrix. So in other words, it either has entries in 0, 1, 2 or 0 plus minus 1. So we say 0 plus minus 1 because this is going to help with noise growth in the FHE scheme. And this is going to be a client-side operation, so none of this has to be encrypted, but just to kind of walk through the operations, the client's going to take this GIMP, which again is public, they multiply it with their input vector X, and they take this operation modulo 3. So they now have a vector dimension 192. There's now this decomp function. I'm not going to talk much about what this function does, but we can kind of, for this talk, we can kind of think of it as mapping from 192 ternary entries into 256 binary entries. And this gives us a binary vector Y with dimension 256. So in the second step, we're going to evaluate the pseudorandom function. So very similar to the weak pseudorandom function before, we have this key A, this matrix key A, matrix key A. And we multiply this with the vector Y, and we receive a new vector R, which is taken modulo 2. This has to be done on the server side. So for the OPRF, we have to assume that Y here is encrypted. And so the result R is also going to be encrypted because the client is going to, by this point, have sent some data to the server to evaluate. The third step is that there's, again, another public matrix G out with slightly different dimensions to the previous matrices. So GIMP and G out can be kind of think of it like encoding matrices that are kind of moving the various inputs to different domains that we want them to be in. G out, again, could effectively be thought of as a random ternary matrix. And there's a typo here, xi. So R here, Ri should be in 0, 1. And we perform this multiplication, we take this modulo 3. Okay, so between these two slides, so between slide 20 and slide 21, this vector R, we have to have performed some bootstrapping to switch the plain text modulus here of this vector from 2 to 3. The reason we do this is actually for efficiency reasons, so that we can perform homomorphic operations on these ciphertexts without worrying about having to perform bootstrapping operations on the plain after we've performed various numbers of multiplications and additions. So actually, we're not doing any bootstrappings for kind of noise growth during multiplications and additions. We kind of choose parameters such that we can perform them without bootstrappings, and we only perform one bootstrapping in order to perform this like plain text modulus switch. Again, this is a server-side operation. So remember, vector R is going to be encrypted, and the output here, vector W, is also going to be encrypted. And then finally, the final operation is on the client side. We take this vector W, we decrypt it, and then we just evaluate a random oracle over it and get the output of the pseudorandom function as Z. So this doesn't need to be in the encrypted domain other than performing decryption. So just to kind of view this in the full protocol, we actually have an offline step where the client first sends their bootstrapping key. We do this to amortize the cost of these bootstrapping keys are fairly large actually. And so to amortize the cost of this, we move this to an offline step. You can kind of think of this as like a registration step, and it kind of fits with the various applications we consider. So I've kind of just mapped these operations to where they appear on the full protocol. One thing to remember here is that, well, one thing to bear in mind here is that if we want to achieve a partially oblivious pseudorandom function, we can simply replace A with a matrix AT, which is equal to the random oracle of A with the public metadata T, which is known to the server and the client. So there's a trivial way to turn an OPRF into a POPRF. So again, yeah, this is kind of like the full mapping of these operations. And then in the end, the client receives the vector CW and decrypts it and evaluates a random oracle over it to get their output Z. So as I mentioned before, we're going to need a lot of zero-knowledge proofs. So firstly, we need a zero-knowledge proof in the offline phase to prove that this is actually a correct bootstrapping key. We need a proof of the well-formed ciphertext. So this is this pi xy. So this needs to come with the ciphertext. And in order to prove verifiability, we need like a proof pi a of like a proof of correct evaluation to prove to the client that the server's actually performed the correct pseudorandom function evaluation. So I'm not going to talk so much about security here because the security of the scheme should be fairly obvious. Once you, obviously we have to assume the zero-knowledge proofs are doing their jobs correctly, but really in terms of the proving that nothing has been learned about the client input, the encryption, the security of the encryption scheme should manage this. I'm just going to talk briefly about ensuring that the server's key A is not actually learned by the client. So in order to do this, we have to use something called circuit private bootstrapping. So this client ciphertext is actually like a ring LWE ciphertext, so it has an error. And actually, when you multiply this ciphertext with the matrix A, that key is going to be encoded in the error of this ciphertext. So this is a really common problem in like lattice-based protocols. So we need some sort of mechanism. So before the server returns the ciphertext to the client, they need to sanitize it somehow. There's various options. There's noise flooding, which is very widely used, but comes with the downside that if you do standard analysis of kind of like noise growth, you kind of need like quite large parameters to make this work. You need either a very, very small noise or very narrow noise distribution and a very large modulus, and you end up in a situation where you have like kind of a sub-exponential LWE assumption, so it's not ideal. So there's this work at Eurocrypt by Ducar and Stelle in 2016, where they actually show that for some concrete finite number of bootstrapping operations, you can show that you can sanitize ciphertext to a sufficient degree. And then more recently, there's been a work by Klushniak in 2022, where they show that TFHE-based randomized blind rotations, which are kind of, again, I'm not really going to talk so much about it, but they're part of the bootstrapping procedure, can be modified very slightly to ensure that you achieve the circuit privacy after only performing a single bootstrapping operation. And given that we're already in the TFHE-based setting, we're going to assume we're going to take that option. But then just to talk about the zero-knowledge proof instantiation. So there's actually been a lot of work on zero-knowledge proofs in the lattice setting, and zero-knowledge proofs now are very, very efficient. So in order to construct the bootstrapping key and well-formed ciphertext proofs, we can use a combination of this work by Lubashevsky et al. From Crypto in 2022 and recent work on Labrador, and construct proofs that are relatively small in both cases. And actually, these can be combined and amortized into a single proof, which is quite nice. In terms of verifiability, things are a little bit unclear, and this is why we get more into the realm of novel heuristics. We found that trying to experiment with Starks or Snarks led to unfavorable costs. And we thought it might be a useful exercise for the community to start trying to exercise the boundaries of what's possible with lattice-based verifiability arguments. So I'm going to talk a little bit about them now. So our idea is based on kind of an idea that was also in the previous work of Albrecht et al. At PKC in 2021. The server publishes kind of multiple checkpoints, which are almost like known answer tests for the pseudorandom function, and proves that these somehow these evaluations have either been performed correctly, or that maybe it's a trusted setup or something. So the clients have these known answer tests. what they're going to do is they're going to batch a number of real inputs together. So this is what their X1, X2, X10 are. And then they're going to include kind of these known answer tests within this batch and then shuffle this whole vector together. So you have these X stars or X asterisks, which are the known answer checkpoints. But because we're going to encrypt our vector of inputs and then send it to the server, these things are effectively blinded. The server is going to evaluate the OPRF on each input and send it back to the client. And the client's going to check each of the known answer tests against the pseudorandom function evaluations that they know about. Okay, and if the server cheated on any of these known answer tests, then they'll be able to see trivially that the server's attempted to do this. Clearly, if the server only cheats on the real inputs but performs the right pseudorandom function evaluation on the known answer test, then they'll get away with proving to the client that they've verifiably evaluated the pseudorandom function when they haven't done. But we're going to show why we think that's a difficult task. So there are two options for the malicious server here. They're either going to have to guess the positions of the checkpoints because each of them is encrypted. So they can't learn anything about whether the thing they're evaluating is a checkpoint or a client intended input. And you can ensure that the server's life is very difficult here if you just publish enough checkpoints and embed enough of them into your queries. And then in terms of a second option, we consider a server that actually tries to construct a cheating circuit, C star. The idea with C star is that what it would do is it would cheat on all inputs apart from when it sees a checkpoint input X star I. Okay, so what the server's doing, what the circuit's doing, it's obviously being evaluated on the encrypted plain text, and it's just checking the value. And if it's a known checkpoint, it will evaluate the correct pseudorandom function, and if it's not a known checkpoint, it will cheat. So the server's task here is to come up with a cheating circuit. Obviously, trivially, this is really easy. You could just come up with any circuit. But the reason why we make this, we think this problem is difficult, is because we're going to force the bootstrapping key, BSK, to only be able to evaluate one level of bootstrapping. So we're going to limit the homomorphic capability of the server, and then we ask the server to break this problem effectively. So remember, I'm just going to show the weak PRF, but it's the same in the full PRF. We have one bootstrapping to switch the modulus here, and we're going to construct the BSK in such a way that only one bootstrapping is allowed. So the server really cannot create a circuit with depth anything higher than 1. And so the challenge here, the heuristic verifiability argument we come up with, is to find a depth 1 cheating circuit that still evaluates the correct pseudorandom function. And we've provided some cryptanalysis in the paper. I'm not going to talk much about it. This is actually a challenge. If you're interested in thinking about these problems, then clearly we'd be very interested if you can come up with a depth 1 cheating circuit that evaluates correctly on the checkpoints and not on the real points without just random guessing. And we think, in essence, if you were to solve this problem, it would actually have interesting implications for FHE circuit design as well, which is quite nice. So it's kind of a win-win situation. So finally, just to kind of wrap up, I guess, I'm going to talk about the efficiency and implementation of this scheme that we came up with. So if we only consider round optimal post-quantum PRFs, so we have the constructions I raised before from Albrecht et al. And Basso, based on ring ODE and isogenies. There's also a more recent construction based on C-side. So the isogeny constructions, the most recent one, are actually very small in the realm of kilobytes, which is quite nice. In the previous constructions were in the realm of megabytes. Classical constructions for context are in the realm of bytes, so we're still quite a way off, as I mentioned before. Our OPRF, so based on lattices and these new kind of pseudorandom function, conjecture pseudorandom functions from Bonnet et al. When we view in the amortized domain, so when we're evaluating 64 points, we can get online communication very low, so lower than previous candidates, which is good. We have this one-time cost of the bootstrapping key, but again, this can be amortized across many evaluations. In terms of the verifiability, so the number of points that we have to send essentially multiplies our communication cost by 16, which obviously has a performance impact. But if we compare this construction to previous verifiable schemes, we're still quite a way lower. We're in the order of kilobytes rather than megabytes, which is nice. But just to compare with the 2#DH construction, which is the one that I mentioned, the prime order group construction that's being standardized by the IETF, where it, 128 bytes, well, 96 bytes online. So this is kind of the performance gap that we're still working towards. So as I said, we're kind of like motivating continued research because clearly there's a lot more to do. And we think that lattice-based constructions still, direct lattice-based constructions could still kind of make a lot of progress towards bridging this gap. So in terms of a concrete implementation, we implemented this in TFHE. There are some caveats here that mean this implementation is not quite a full implementation of our scheme that I'll talk about, but just kind of the headlines. So here are our lattice parameters for achieving 100 bits of security. And in terms of the headline performance costs, our online costs, so that's like the client request, server evaluation, client finalized, are all milliseconds. So we're actually doing very well on this score. Server evaluation is highly parallelized, it should be noted. So there's 64 cores being used here. When you only use a single core, it's more like 7 or 8 seconds, I think. Client keygen is quite expensive as well, but again, this is kind of like an operation we can amortize. And the code for everything that we use in the benchmarking is available online at the link provided. So the disclaimer is that TFHE-RS currently does not actually support a lot of the various core functionality that we assume in our scheme. So in order to perform in order to compute our OPRF without performing a large number of bootstrappings, we actually have to modify the test polynomial that's used for blind rotation in TFHE. And modifying these test polynomials is not, as far as I know, we attempted to do it kind of at a low level within the TFHE source code, and we couldn't really get it to work. Non-power of 2 moduli are also not supported. So the operations we have to do mod 3 are kind of, well, not kind of, but they are simulated. And then circuit privacy and public key compression, which is something we use, are not implemented as well. We actually provide, though, a complete implementation of our whole scheme in Sage, but given Sage's performance kind of overheads, it's not really, we can't use it to benchmark the scheme, but we can use it to establish the correctness of our scheme. So if you want to see that, the whole source code for that Sage implementation is included in the appendix of our paper on ePrint. The only thing I would say is that we don't provide an implementation of the zero knowledge proofs. So just to conclude the talk, so we built, as I mentioned before, we build post-quantum verifiable and partially oblivious pseudorandom functions from FHE. We actually get relatively close to relatively practical costs for the core FHE PRF. So here I'm, avoiding kind of the caveats that I mentioned with TFHE-RS and the fact that we don't have the zero knowledge proofs, but we're less than a second in terms of computation on those core operations, and we're in the order of kilobytes for bandwidth, which is nice. We're a lot closer to classical schemes than we were in the past. The zero knowledge proofs still seem relatively restrictive, not necessarily totally in performance, but implementations we found were quite hard to come by as well. And I think deriving an implementation that's very performant for this setting would be still quite a difficult challenge. Clearly, if someone, implementations here of zero knowledge proofs in the lattice setting would be very valuable for really properly costing our pseudorandom function. We have a lot of heuristic security arguments in this paper. We're kind of at the edge of assuming, of guaranteeing security. We have a lot of conjectures. Here, we obviously need cryptanalysis to kind of verify our findings. It might be that, a particular circuit could be found that cheats for breaking verifiability. The PRFs we consider as well are obviously not based on typical standard assumptions. And so working on cryptanalytic work on these kind of ideas would be valuable as well. In terms of future work, Clearly, improvements to FHE, the TFHE library, to the TFHE scheme would result in direct impact on our work. But we actually think that rather than continuing to build these schemes from FHE, our work kind of motivates researchers to return to direct constructions based on lattices and even based on isogenies and say, can we improve these schemes further? If we can achieve this performance from FHE, surely there is a direct approach to it that can be made more efficient, given that FHE is more like a black box primitive than it is an optimized primitive for very specific functions. But clearly, both directions are still interesting. And I think given the recent work on standardization of these primitives, there's a lot of motivation to continue trying to build oblivious pseudorandom functions for various applications. So just to finish, thank you for listening. And here's my email and the paper, link to the paper. Thank you.